So this video will continue section 6.5 on equilibrium, and we will focus on the magnitude of the equilibrium constant. So we know now how to write the equilibrium constant expression for a given reaction, and we will learn how to calculate the value for the K for the equilibrium constant. And this value has a meaning. And so what is that meaning? So when K is much greater than 1, that means if we recall what is the expression for the equilibrium constant, it's the concentration of product over the concentration of reactant. And so if K is much greater than 1, that means the numerator is large, much larger than the denominator. If the numerator is large, it means the concentration of the products are larger than the concentration of the reactant. So that means you have more product when you have reached equilibrium than you have reactant. And so the equilibrium lies to the right and favors the product. That's how we interpret a large K value. Now, if K is much less than 1, so again, if we look at the expression of K, it's the concentration of product over concentration of reactant. If it is less than 1, that means the denominator is large. And when you divide by a large denominator, you get a value that is much less than 1. So that means the concentration of the reactant is much larger than the concentration of the product. And so that tells you that the equilibrium lies to the left and favors the reactant because they are in a much greater number than the product. And when K is around 1, and 1 is really a simplified value here because it really goes from a K value going from 0.01 to 100, right? It's not just around 1, it's, 1 divided by 100 and up to 100 is considered around 1. So that tells you the concentrations of the product is similar in magnitude to the concentration of the reactant. They are both present in a similar amount when you have reached equilibrium. So that tells you it's like a real equilibrium where you have both reactant and product in similar amounts. Because you cannot neglect the concentration of reactant versus product or vice versa. So this table summarizes what we just said. Depending on the value of K, you can tell the position of the equilibrium, if it favors the product or the reactant, or if both reactant and product are present at equilibrium. So if it's a large value of K, we have more product and the equilibrium lies to the right. If we have a small value of K, less than 1, then we have more reactant and the equilibrium lies to the left. And when it's close to 1, and again, close to 1 here is, between 0.01 and 100, then you have both reactant and product present at equilibrium in, values that cannot be neglected in reference to the other. So let's go through a learning check that will use this information. So for each Kc, equilibrium constant here, indicate whether the reaction at equilibrium contains mostly reactant or product. And so here the first reaction has hydrogen in gas phase plus fluorine also in its gas phase in equilibrium with 2 molecules of HF also as gas. So we have this equilibrium, and the equilibrium constant has a value of 1 times 10 to the 95 So this is a very, very large value, right? It means it's 1 multiply 95 times by 10. So it's a very, very large value. So when K is much greater than 1, it tells you the concentration of product is very, very large compared to the concentration of the reactant. And that means the equilibrium contains mostly mostly product and lies to the right. And honestly, this is not really called an equilibrium at that point. It's more like considered a complete reaction with only an arrow going from left to right to be really truthful. Second example of reaction, it's the reaction that is making ozone from 3 molecules of oxygen in their gas phase is in equilibrium with 2 molecules of ozone, O3, in their gas phase. The equilibrium constant has a value of 1.8 times 10 to the negative 7. So times 10 to the negative 7 means you divide 1.8 7 times by 10. So it's a very small value, much smaller than 1. And when we have a Kc that is much smaller than 1, that tells you the concentration of the reactant is very large. And so the equilibrium contains mostly reactant and lies to the left. So it favors oxygen in this reaction rather than ozone. So let's learn how to calculate the equilibrium constant for a reaction. So the first step is to write the expression for the equilibrium constant from the balanced equation. So here we have a generic form of an equation here that says molecule A2 plus molecules B2 is in equilibrium with 2 molecules AB. So the equilibrium constant of this reaction would be concentration of product. So here it's AB, concentration of AB squared, because AB has a coefficient 2 in front of it, over concentration of A2 times concentration of B2. And A2 and B2 have a coefficient of 1 in front of them, so they are not raised to any power other than 1. So that's the expression for the equilibrium constant. So the next step is to be given the values of the concentrations, and here they are. Concentration of A2 is 0.25 molar, B2 is 0.25 molar, and AB is 0.50 molar. Remember how brackets are meaning concentration in molarity. So that's why the values are in capital M, which symbolize molarity. So the second step is to substitute the given concentration in the equilibrium expression and calculate the K value. And so it means K is equal to concentration of AB squared. So AB has a value of 0.50, and you can drop the molar unit. So 0.50 squared over concentration of A2, so 0.25, times concentration of B2, also 0.25, multiplied together. And so if you multiply, so if you take the square of 0.50, it's 0.25 in the numerator. And if you multiply 0.25 together, it's 0.0625. And then 0.25 divided by 0.625 as an exact value of 4 in your calculator, right? We still need to pay attention to significant figures here, and all reactions were given with 2 sig figs, right? 0.25 has 2 sig figs, and 0.50 has also 2 sig figs, because that 0 is significant. The 0 after the 5 to the right of the 5 is significant. So we need to keep 2 sig figs. And here the calculator answer is 4, exactly 4. So it's up to you to know that you need to add 0.0 to say 2 sig figs here, 0.0. Notice how the K has no unit. The K value has no units because the molarities cancel, but sometimes here they cancel nicely, but sometimes it's not the same amount of molarity on top than on the bottom. And so to simplify things, K is set to have no value, no units, sorry, no units. So you will never give a unit to the K value. So here it's equal to 4. So it's not on the slide, but if I were asking you, so what do you think? Is this K value indicating that the equilibrium is favoring the product, the reactant, or are both reactant and product present at equilibrium? And you should answer that both reactant and product are present, because 4 is a value considered close to 1. You know, it's less than 100 and more than 0.01. So it's considered that reactant and product are both present in similar magnitude at equilibrium. And you can verify that by looking at the concentrations. Indeed, the concentrations of A2 and B2 are 0.25, and it's not negligible compared to the concentration of AB, which is 0.50, right? These values are just half of 0.50, and it's not negligible. They all are meaningful. So we have an equilibrium where we have all reactant and product present. So let's go through this learning check to practice calculating the Kc value. So you're given the chemical equation, and it's methane, CH4, a gas, plus water as a gas, in equilibrium with CO, carbon monoxide, a gas, plus a 3H2, a gas, and that's hydrogen gas. You're given the equilibrium concentrations for CH4, CO, H2O, and H2. So you want first to write the expression of the equilibrium constant for this reaction. Kc, remember, is the concentration of product over the concentration of reactant. And so here we have two products, CO and H2O, H2, sorry. So you will have concentration of CO times concentration of H2 cubed, right? The concentration of H2 has to be cubed because you have 3 molecules of H2 produced. So the coefficient of 3 becomes an exponent for the concentration of H2 over the concentration of reactants. And here we have CH4 and times H2O. And both of them have coefficients of 1, so you don't need to raise to an exponent here, to a power. So that's the expression of the equilibrium constant. Now let's substitute the values for the concentrations. Remember how brackets means a concentration in molarity, and that's what we are given. The concentrations are molarities. So if you substitute the value, it looks like this. Concentration of CO is 0.81 times concentration of H2 is 0.28 to the cube, raised to the cubed, over concentration of CH4 is 0.13 times the concentration of H2O is 0.53. So let's enter this in the calculator. And here you have to be careful how you use your calculator. So listen carefully. It's 0.81 times 0.28. You can use the caret key, which is the hat key, if you will, next to the x-1 key and above the x squared key if you use the TI30X2S calculator, of course. But you want to find the power key, right? And then 3 for the cube divided. And here, either you divide by each denominator or you open the parentheses. After you divide, you open the parentheses and you do 0.13 times 0.53. Close the parentheses, enter. Your calculator answer should be 0.25807, etc. Here, all concentrations are given with 2 sig figs, right? The zeros are not significant. So 2 sig figs means you keep, so 0.0, 0 point. You keep the 2, you keep the 5. What comes after the 5 is an 8, so you round your 5 to a 6. And that's why the answer is 0.26. I want to mention that to calculate this, you can also do 0.81 times 0.28, cubed. And you can divide by 0.13 and divide again by 0.53, right? This is another way to use the calculator and have the correct answer. So make sure you pay attention to how you use your calculator. And so then the question is, will the reaction favor products or reactant when the Kc value is 0.26? So again, this is a value very close to 1, right? It's between 0.01 and 100. So it's considered a value close to 1. And so when it's like that, you cannot neglect any of the concentrations, and both reactant and product are present at equilibrium. And this is confirmed by the values of the concentrations, right? There is a way to verify that by looking at the concentrations at equilibrium. They're given to you here. And you can see that all these values, you cannot neglect any of them versus the others, right? They are all, meaningful enough to not be neglected. So then that confirms that both reactant and product are present at equilibrium. So let's do another learning check with this new chemical equation that has phosphoric acid H3PO4, it's an aqueous solution, plus 3 OH minus, the hydroxide ion, it's also in aqueous solution, is in equilibrium with 3 molecules of water as liquid, plus the phosphate ion, PO4 negative 3, and they are aqueous because they are dissolved in water. I want to emphasize that when we have water being formed from aqueous solutions like that, water will not be aqueous. Water is the solvent. Aqueous means that it's dissolved in water. So water is the solvent. So when you're forming water, it's a liquid. You do not have aqueous for water. It's not proper. Okay, so we have this equation. We are given the equilibrium concentrations of the reactant. They are OH minus 3 molar, the phosphoric acid 1 molar, and the phosphate ion has a concentration of 1.2 times 10 to the negative 8 molar. So what is the equilibrium constant for the reaction? So you want to write the expression before you do any plugging of value, right? It's important to have a correct equilibrium constant expression before. So the equilibrium constant has the concentration of products over the concentration of reactants. And so here, notice how water is a product, but it's a liquid. So as a liquid, it will not be included in the equilibrium constant. So in the numerator, you will only have the phosphate ion, and it will not be raised to any power because it has a coefficient of 1. So it's going to be PO4 over concentration of H3PO4, the phosphoric acid, times the concentration of the hydroxide ion raised to the third power, right? So OH minus is cubed because we have a coefficient of 3 in front of OH minus. Next, you want to plug in the values of the concentrations. The concentrations are given in molarity, which makes sense because the brackets here symbolize concentrations in molarity. So it's 1.2 times 10 to the negative 8 for the phosphate ion over phosphoric acid is 1 and the hydroxide ion is 3 to the third, right? Don't forget to raise the 3 molar to the third power because OH minus is cubed. So in the calculator, you do 1.2, you know, do your second function for the EE key, negative 8, just type the exponent, divided by, and dividing by 1 is not necessary, so you can directly divide by 3 raised to the cube. And the answer is 4.444, many fours after that, times 10 to the negative 10. Don't forget to watch for scientific notation here. So times 10 to the negative 10. And remember how K has no units, so there is no units here. We keep 1 sig fig because the hydroxide ion and the phosphoric acid, they both have only 1 sig fig in their concentration, you know, 1 molar and 3 molar. So we keep just a 4 times 10 to the negative 10. No units. So will the reaction favor products or reactant, given that value for K? So 4 times 10 to the negative 10 means you divide 4 10 times by 10. So it's a very, very small value, much smaller than 1. When K is much smaller than 1, this means your concentration of reactant is much larger than the concentration of the product, right? The denominator is much larger than the numerator, which means we have much more reactant. So the equilibrium will lie to the left and favor the reactant in this case.